In two-phase method, we are going to be using the same concept that we used for the big M, except that we will try to avoid the problems that are associated with the use of M. We said that M is a very, very large number. If the other numbers in a LP are small numbers, large numbers tend to dominate the results. Let's break down our intention. Our intention is first to get to a feasible point and then optimize. To show you the difference in visual terms, this is what is going to look like. And of course, this is a hypothetical situation. It may not even be correct, but anyway. Let's say that you have a problem which looks like this. And this is your feasible solution in 2 dimensions. This is your feasible solution. And this is your Z. And this is your Z. And the direction of it increases that direction. So maximum of this problem is going to be, what big M does is that it will try to maximize. So it is going to go toward this point. Starting from where? Starting from here. I don't know. It may go this way. It may go this way. It may go this way to this point. It may go this way to this point. It may go this way to this point. It may go this way to this point, and then it goes that way to that point. May. I'm not saying that this is going to happen, but just consider this case. What does that mean? It means that we started infeasible. We went to another extreme point, which was infeasible. We went to another extreme point, which was infeasible. We went to another extreme point, which was infeasible. We went to another extreme point. It became feasible before it became optimal. So 1, 2, 3, 4 tableaus it took before I actually got rid of M's in my problem. Before I got rid of M's in my problem to find a basic feasible solution. And all the time I had to do calculations for M all over at the 0. Which some of you that may have tried it would realize how tedious and difficult it becomes working with these numbers and so on. So this is a drawback of the problem. Again, I don't know whether this is the case that is going to happen. but I'm saying that this is a possibility. And in fact, it may be that you have to stay infeasible until you hit the optimal solution. So two-phase would say, well, let's break this down into two separate problems. One, let's find a basic feasible solution first. So the fastest way that I can get to a basic feasible solution becomes my intention. And in this case, I may go here and here to this point, or I may go actually here and here to that point. In both these cases, I did not pay any attention to the actual z. My z was a different thing. My z was to get to the feasible point. And what causes the feasibility are r's. So my intention was to get rid of r's as soon as I can. Now, the other problem with the big M is this. Let's say that I started big M and I actually went from this point up to this point. And from this point to that point. So in two tableaus, it became feasible. And then I went to here and to here and down to here to get to the optimal point. I'm working with the feasible tableaus. But I'm still doing the calculations for M's. Where? Under R's. All the M's are under R's. So you keep doing calculations for M's, although you don't need them. Because in this technique, you keep the whole thing together. In the other one, the moment that you become feasible, you will drop all the R columns. So it becomes even more efficient. Now, this at the outset, the big M at the outset, sounds better because you're moving toward optimal solution. Two-phase, no, it doesn't care about where the actual z is. It is trying to get to the first feasible solution. But in practice and in reality, and the ease of it and efficiency of it, two-phase is the one that they always use. So let's set up a problem to make sure that we will have an optimal solution. With x1 and x2 greater than or equal to 0. Let's give you 3 minutes such that you can write the big M setup for this. That's how the big M setup is. And this is going to introduce X2 into the next tableau, and R1 is going to leave. By coming X2 into the basis, the next one will be this point. That's the next tableau value. Why is it not that value? Because you move to an adjacent extreme point. Now from here, it might go this way or it might go that way. We don't know. But that's how it looks. In two-phase, this is what we are going to be doing. We are going to break the problem into two phases. At phase 1, we say our intention is to get rid of the artificial variables, which means to find a basic feasible solution. As such, we are going to change temporarily our objective function. We will create a new objective function. This new objective function is summation of all the artificial variables that we have. If we have one artificial variable, it would be z, we call it z prime, equal R1. If we have 2, it would be R1 plus R2. If we have 3, it's R1 plus R2 plus R3. So this new objective function is simply the summation of all the artificial variables that I have introduced into the problem. And remember what our goal is: to make the artificial variables become non-basic, become 0. So the intention becomes, how do I get these artificial variables to become 0? I have added them up, and I say, if this is supposed to be 0, then summation of them should be 0. Right now they have values. How would I make sure that they become 0? I will minimize that sum. So phase 1 objective function is to minimize the summation of artificial variables. So I'm going to set up my phase 1 problem. Phase 1 problem consists of a new objective function, I call it z prime, equal to the summation of all the i's that I have. In here I have R1 and R2. So this is going to be R1 plus R2. And then I will minimize that, subject to original constraints that I have. So it would be this subject to that. So what is the objective function, the 0 in here for this problem? It is going to be, there's a -1 here, there's a -1 here, 0, 0, 0, 0, 0, and 0. And I kept the problem as minimization. I didn't change it to maximization. If you change this to a maximization, these values will be plus plus. So whatever you want to do, make sure you are consistent. Don't mix them up. Now if you wanted to multiply this by a negative sign and convert it to a maximization, we would write minus z prime in here and we will change that to plus and plus, and then we will follow from that point on. But let's practice with the minimization also. At this stage, you should be comfortable to do that. Yes?
What would the right-hand side be for the 0? Would you just do 0?
0, yes. Thank you. So this setup. Now, with this, you have to make sure that the issue of legitimate tableau comes into mind. This tableau is not legitimate. Why is it not legitimate? You look at R1 and R2, and they are supposed to be 0, and they are not. We will try to get rid of those by multiplying this row by 1 and adding it up there, and this row by 1 and adding it up there. Together we can do the same thing. We will multiply this and add it up there. So there would be 2 and 0 plus 0, that would be 2. This will be 2. 1 and 3 plus that would be 4. 0, 0, that is 0. 0, 0, that is 0. 0 and minus 1, that will become minus 1. Minus 1 and 0, that will become minus 1. 1, this becomes 0. And minus 1 becomes 0. And this becomes 7. That value of 7, these values that you see in here, has nothing to do with the original problem. However, if you look closely at your big M, you might be able to see some of those numbers. Where are they?
Coefficients of M.
There are coefficients of M in there. Okay? So this is very much close to what you can see. And instead of multiplying minus 7 by M, minus 7 by a million or 10 million, instead of having that number, you have just 7 or something like that. So these are very much like that. This is a minimization problem. The difference between minimization and the maximization is in the selection of the entering variable. The rest is exactly the same. What do we do with the maximization problem? We will look for the most negative in the 0. In this case, we are going to look for the most positive in the 0. So you will look around here, and lo and behold, again, x2 is going to be our entering variable. And if you do this stuff, this is going to be your leaving variable. After you process this, you will end up with a new tableau. Could you spend 3 minutes and find me the new tableau? Now, let's see what I write underneath this tableau. And you can write it on under the first tableau too. Solution. I'll write them here, but you need to write them underneath. Solution? Who knows where that number 3 came from? Other than the calculation in here. What does it mean in terms of the real problem? That's your Z prime. Plug in R1 and R2 in here. Plug in R1 and R2 in here. You will get 3. That's what that means. We will look in here and we will identify whether the optimality conditions are satisfied. To look at the optimality conditions, we will look at this row. I have X1 a candidate and I have S4 a candidate. Which one should I select? Why? Because it has the most positive value. In here, what is the intention? To get rid of R's. Okay? To get rid of R's. So if between the two, one of them doesn't result in the R going out of the basis, select the other one if it does. Because we want to get rid of the R's. The moment that you get rid of the R's, you are optimum here. Because that becomes 0. So let's, for example, let's look in here. Let's say that we wanted to select X1. We wanted to select X1. That's negative, this is 0. So 4 over 1 and 3 over 2. R1 is going to be the leaving variable. Let's look at S4 in here. 4 over 1 and 3 over 3. Still, R2 is the leaving one. But if you had a case which you had several, pick the one that causes the R to leave the basis. The moment R leaves the basis, you are optimal. Why are you optimal? And I'm not even saying feasible. You're optimal for this problem. Okay, which one would you like to select? S4, whatever you say. And that is the leaving variable. So can you do the tableau for me in 3 minutes? So, where did we go from here? We still stayed at x2 equal 2. We still stayed on the x2 column, but we went to that point, which is now a feasible point. We went there, which is now a feasible point. That's our That's our feasible region. Remember that I told you you also had the option of entering x1? If you entered x1, where would you go? You would have an x2 and x1 in here. Where do you think you would go from here? You will go to this one. Now in 2 dimensions you can see all these things. More than that is difficult. You just have to have the concept. This is how the concept works. So we do have now a solution which is, the key word is, which is feasible. The moment that you reach a feasible solution, there are several clues in the tableau. First of all, if you look at the zero, the z prime row in here, everything is going to be 0 with the exception of 2 minus 1s underneath the artificial variables. Always it would be like that. If you convert that to maximization problem, everything will be 0 except underneath the artificial variables that you would have 2 plus 1s. 2, 3, as the number of artificial variables that you have. The next thing is z prime value is going to be 0. That's where you reach a feasible solution. The moment that you reach a feasible solution, z primes becomes 0. As soon as you hit this, you would say end of phase 1, start of phase 2. Now, a question right here. If you ended up with everything in here to be negative, like this case, but you still have r's in here with the values other than 0, what would you do at that point? You have all negative numbers in here, so you can't go any further, but you still have r's in here with values greater than 0. That's when you declare the problem infeasible. You stop analysis. You say the problem is infeasible. So in this case, the problem is feasible, and we want to set up the phase 2 tableau. In phase 2 tableau, we are going to replace, don't touch anything else, we are going to replace the z prime row with the actual, the original 0 in standard form. Important, in standard form. So I'm going to erase that prime here, that prime there, all these numbers in here, all these numbers in here, and we'll put the original 0. Another thing that I will do, I will drop the column of artificial variables. So I'm going to erase that and that. The original z prime row is minus 3 minus 4, 0, 0, 0, 0, and 0. We have found our basic feasible solution. We are now solving the original problem. So the same way that we did, we will rewrite this in terms of standard form, z minus 3 minus 4, and that's what I have in here. There's no s's in there, so that is how it is. And the right-hand side is 0 for this. Then I will go back and I will double check, is this a legitimate tableau? And as such, where would I look? For the identity matrix under basic variables. S1 looks okay. S2 looks okay. S4 is okay. X2 is okay. It's not okay. There is a negative 4 in here. What should it be? It has to be 0. How would I get rid of that? Multiply this row by 4 added up here. Okay? So multiplying this by 4, I would get 8. By 4, I would get minus 4/3. By 4, I would get 0. By 4, I would get 8/3 minus 9/3. That would be minus 1/3. Because this is the regular simplex now. And you all know how to do regular simplex, don't we? We all know that. Okay. So, big M, two-phase. Big M, two-phase. There are two techniques. They are not separate algorithms for themselves. The algorithm is simplex. Simplex algorithm is the one that we are using. These are two techniques to start the simplex tableau when we don't have a readily available solution. That readily available solution was what? The origin. If origin is not there, and when would that happen? Usually when you have greater than or just equal sign. On those cases, you need to use artificial variable. Anytime you use artificial variable, you have to use one of the two techniques. Big M, two-phase. The purpose of these two techniques are to get you started on a basic feasible solution for the simplex tableau. And when you have a basic feasible solution for the simplex tableau, now you can continue with whatever step is needed. Again, this is a more efficient because it avoids those large numbers associated with the m's, and also it doesn't carry the calculations of artificial variables throughout the tableaus. This is a much easier tableau to work with. So in here, what would be the entering variable? S3 will be the entering variable because it's the most negative. And then you say, Dr. Salimian, up to now you kept saying most positive. What happened? That was a minimization problem. This is a maximization problem. So we will be looking for the most negative. We will be looking for the mean ratio. And we carry an iteration. We carry it out until we get an optimal solution. X1, R2. Z prime, 1, 0, X1, X2, S1, R1, R2, and so on. Seven and 0, this is Z prime, and that is 0. At the end of phase 1, we reach this tableau. Can we declare end of phase 1? Yes. R2 is still here, but its value is 0. R2 is still here, but its value is 0. So you can go to the next tableau, end phase 1 here, and go to the next one. But when you go to the next one, what happens? You drop R1, but you cannot drop R2. Why? Because R2 is a basic variable. So you carry R2 into the phase 2. Or this is what you can actually do. Remember, all these numbers are going to be 0. What does that mean? Think about it for a second. Is x2 a basic variable? Is x2 a basic variable? It has a 0 in here. What does that mean? It means, so there is an alternative solution. So there is an alternative solution. So there is a way to get rid of this one too. How would you get rid of that one? Select one of these variables. Don't end your phase 1 if it makes you confused. Don't end your phase 1. Select one of the variables and take R2 out of the basis. That way it will be very easy for you.